Three case studies showing ICT supporting hard-to-teach topics in secondary science. Using data logging equipment to capture real-time experimental data, using curriculum resources on a virtual learning environment, and using comic strips and animations to illustrate an investigation.
We've been doing data logging at this school for since 2003, and we have a whole collection of data loggers. For example, today we're going to be showing the use of a sound sensor, a carbon dioxide sensor, an oxygen sensor, a humidity sensor, a light gate, and all these things, just pretty much like every data logger we have here, can be connected to a laptop. And not only that, we also have these PDAs, which means we can attach any of these sensors to it and we can do some remote sensing. But the beauty of it is that the pupils can collect data, use the data, interpret the data and evaluate in real time what they're doing, and that's what the real benefit is of data logging. And what you're going to have to do is
Science teacher Paul Preece is going to demonstrate a classic combustion experiment to his Year 7s, but with the addition of some data logging equipment.
We have in there a thing that detects water, a sensor which detects oxygen, and we have the sensor at the bottom which detects carbon dioxide. And the computer is going to plot for me how much oxygen is in there, how much water is in there, and how much carbon dioxide is in there. So I'm going to connect these sensors up first. So first of all, I'm going to attach my oxygen sensor here, my CO2 sensor, and my water sensor. So our carbon dioxide is not changing, our water is not changing, and neither is our oxygen, okay, staying the same. So I'm going to put the candle in. I'm going to watch what's happened and see if you can use very quickly the ideas of what happens with the graph to explain what is going on, okay? So what's rising?
The blue.
Moana?
The humidity.
The humidity, good. What's that detecting?
The water.
Thank you, Cameron. Okay, so we are detecting water. What is happening to the amount of carbon dioxide inside the bell jar?
It's increasing.
It's increasing, thank you. So the carbon dioxide level is going up. The oxygen level is going
down.
Down, thank you. Okay, so the oxygen level is going down. The humidity's gone up high. Look how high the humidity's gone.
Ooh.
Okay, so what does that mean we are using up? Moana.
Is it the oxygen?
Well done, Moana. It's the oxygen. What are we producing?
Is it carbon dioxide?
It is, well done. And what else are we producing? What else are we producing? Think about what's the other one that's gone up?
Is it the humidity?
Humidity. And what does the humidity detect? You drink it?
The water.
The water. Thank you very much. Okay. I know the candle's gone out. Okay, thank you. There's a lot of taken on trust and on what the teacher says when you talk about combustion. So demonstrating that how the water is produced and the only thing that is actually happening is something is burning. So you can actually show the water levels increasing and show that the carbon dioxide level is increasing and showing the oxygen level is dropping is a really crucial point. And then they start to appreciate looking at a graph to see how things change, that if it's going up, it must be being produced. If it's going down, it must be being used up. So they start to now appreciate what a chemical reaction is, what reactants are, what products are, even if they don't fully understand all the language we would normally use when we're talking about science. So that's the benefit of using the data loggers.
These Year 8s are going to use handheld PDAs connected to a sound sensor to investigate sound levels.
Okay. You should have a blue screen that looks like that. What we do then is we go to the start, and then you go to Programs, once you hit the start button. And then there's a folder called Sensing Science. If you click on that, click on Graph, and then you should get a graph being produced. Okay? It's playing now. PDAs are really, really useful pieces of kit. And what's nice about them is that they know how to use technology. They don't have any problems with that. And the idea you can plug and play straight away into a sensor, and you can start to actually take actual measurements, and it plots the graph for you in real time, means that you can really go to town on kind of analysis. I would like you to try and hold the sensor next to your faces and then see what decibels is a whisper, a conversation between two people, a group talking, and a clap. Okay?
So clap in decibels is 86.3. Yeah.
For the whisper, we had 75.4.
Can somebody tell me, please, what kind of decibel level we get for a whisper?
75.4.
Brilliant, thank you. So we have about 75 dBA, okay, decibels. Okay, next one, we got a conversation between two people.
About 92 decibels.
92 decibels, dBA, okay. And we have now a group of people talking.
We got 110.
Thank you very much. Straight away, they can start to attach numbers to noises that they're making. So they can have a whisper, they can have a shout, they can have a clap, and they can then associate what those sounds do as to what their decibels are. It's almost like sometimes you're trying to dampen down their enthusiasm a little bit because they go mad for it, because they enjoy it so much. But that's what, as science teachers, we love. We love getting students engaged in their science, understanding science, wanting to learn more, investigating. There we go. All right. And then
These Year 9s are going to investigate the motion of a trolley rolling down a sloping ramp.
and I can work out how fast it's going at different points. Now, this is where the technology comes into it. Okay? Now, I'm going to have to do this experiment time and time again because I want to know, after it's travelled 20 centimetres, what its speed is, after it's travelled 40, 60, 80, 100. So how am I going to do that?
Take photos, and the time distance between them is, I don't know.
Good idea. That's a really good idea. I could take photographs, okay? Yes. What about you? What do you think? Come
on. Well, would you put laser beams on the track, and then as it breaks the laser beam, see when, and then when it breaks the other one, see when that happens, and then get...
That's a clever idea. And in fact, it's very close to what we're going to do. Well done, Daniel. Okay. So let me show you what we're going to use. These things are called light gates. What they have inside here is a small little light sensor on that side, and this one gives out light. Now, when we connect this to the computer, as the truck falls down the ramp, it will cut the beam of light, pretty much like Daniel was saying, okay? And then, when it's gone past again, it will then detect the light. If we tell the computer how long that piece of card is, it will automatically work out for us how fast the vehicle's going, okay? So what you're going to do is, once you've set your ramp up, you're going to choose at what distances you're going to measure the speed, and then you let go, and the card has to cut the light beam without hitting it, okay? That will be for 20. Then you'll do the same thing, making sure I drop it from the same point again, but this time I'm going to hold the light gate at 40. All right, guys, off you go. They've already bounced it. This is the first time they've used the light gates, and setting them up takes a little bit of time. Using it with quite a large piece of equipment, I mean, you're talking about a lot of skills here. You're talking about coordination, you're talking about management, you're talking about group skills. All these things have got to come all at the same time in order for this practical to work. And I think, you know, they did really, really well, and they were able to actually work as a group, assign roles to certain people. You do this bit, you do that bit. And they did that really well. And using the equipment for the first time, within 15, 20 minutes, once they knew what they were doing, that's it. And that's the beauty of the youth today. They can do that. They're so ready just to pick up and adopt new technologies. They don't have a problem with that.
So that's 20, that's 60, that's 1 metre.
It's not a difficult concept. What it is, though, it's a chance to actually collect data and interpret data and actually get reproducible results of which they can be critical about in real time.
Right at the top for 20 centimetres, you just have 1.172 metres per second as an average speed. Right, and at 80 centimetres, we have 1.861. So we must deduce that it will accelerate.
And how would they have done this without the light gates?
You'd have to do it by eye and use stopwatches, things like that, so it'd be a lot harder. Where's our line graph?
Third one.
Yeah. Line.
We need
Next.
Or maybe a scatter.
Series in.
Very good, I like it. That's a nice graph. Yeah, the fact that they could do it so easily, so quickly, and get results, and with one short lesson, get a nice graph and able to come up with a prediction.
So you could say that there'd be a good correlation.
There's a good correlation between the two, yeah. And it's that skill that is very difficult to teach, and it's very difficult to get that idea across, and that's the hard to teach part of the topic.
This morning we're going to have a look at changing another variable in rate of reaction experiment.
Chris Mason is head of science at Salandine Nook High School in Huddersfield.
Now already you should be starting to think about what effect...
He's working with his Year 11s to investigate rates of reaction.
Can anybody predict what we think might happen if we vary the temperature of the sodium thiosulfate? Gina?
If it's warmer, then the reaction will happen quicker.
OK, if it's warmer, the reaction will happen quicker. That's good. Can anybody give a reason why they think that might happen? Stephen?
The particles will have more energy, so they'll collide and have more effective collisions, which means that they'll react.
Yeah, yeah. So they'll react quicker. So the key word that we were using there was effective collisions.
The practical session involves investigating the reaction between sodium thiosulfate and hydrochloric acid, which will be part of their coursework.
49.
Here, the students carry out this reaction at different temperatures, measuring the differing times the reaction takes to complete.
1 minute 40.
The reaction is complete when the black cross on the paper is obscured by the cloudy precipitate. Once they've got a set of results for reaction time against temperature, they move to the computer room.
What I'd like you to do is exactly what it says on the board. Use the smart book, and there's a link to the smart book there, C6. It does work to help you interpret your data. And then, key point here, remember that in your coursework, you will need to fully explain why the rate of reaction changes. And on page 39 in your notebook, I've actually put the mark scheme from the exam board, which shows you how far you need to go to get the full marks.
The students then log on to the school's VLE to search for information that will help reinforce and explain what they found out from their practical investigation.
Well, in the shared network that we can all get to, Mr. Mason's got a folder just for Year 11s. And then there's usually like internet links and stuff on that help us with answering the questions and stuff.
We've got like worksheets that we can work through, and then on some of the worksheets we've got like links to PowerPoints just to help us and like help understand the work that we've been set.
There's just like all different worksheets like to help you, and like what we do in lessons, and just like put on there and then Sir does them on the board and just explain more.
What we decided to do as a staff team was use 21st Century Science, which is the Year 10 and Year 11 GCSEs, and for staff and for students we decided to break down each of the topics into smart notebooks, and what we've done is basically broken down the lessons and included all the resources that you would need to successfully teach these lessons in the attachments on the side. We've also included the GCSE mark scheme for additional science. The hope being that they'll be able to self-assess where they are on the mark scheme and also find what they need to do in order to get to the higher levels. We also have got some live links to the Alchemy website by the RSC, and on the simulations page, which a lot of the students are using today, we'll link to external simulations.
There's just a page on here which is a link to this website, and it just like shows you like if the temperature's cooler, the reaction's slower, and if like you make the temperature higher, the reactions gets faster and it turn green when they've collided together.
We found that using textbooks in lessons and allowing students to take textbooks home resulted in a high cost basically, but they've always got something which they can pin their understanding around. There is a very clear lesson framework. Yeah, we found the software useful because, as you can see, we can vary the concentration of the particles quite easily. We can change the temperature, giving the particles more or less kinetic energy. This goes a little bit deeper into particle theory and hopefully helps the students understand the difference between an ineffective and an effective collision.
You can like change like things like the temperature and different variables like the concentration, and then see how many like collisions and reactions occur. This is the reaction time, and in 12 seconds there's been 26 collisions but only 11 reactions. If you put the temperature all the way to 10 and do the same amount of time, there's much more reactions, so it makes more effective collisions.
We find it's incredibly powerful in helping students to visualise the mechanics of the reactions, which then feeds back into their coursework and hopefully will help them succeed and get the highest possible levels.
Increased temperature, the reactions will happen faster because the particles get more kinetic energy from the heat, and when they collide, a reaction will occur.
And the work they're doing today and in previous lessons has been choosing one of these particular techniques upon which they're going to base their coursework. So we're doing preliminary work at the moment, so we're really giving them a sound grounding of the choices to make about variables, about ranges, about equipment, and then the interpretation of their preliminary experiments, so that when they go on and actually do their final investigation, they have a much higher chance of being successful and getting the marks of which they're capable.
I think it's better, it's easier this way than a teacher telling you, because you can relate to it more. It's a bit easier. Yeah, because you can actually see it and you can look back at it. Exactly.
Visualise it as well, rather than just words. You can see what's going on.
Yeah, it's because you can look back at it whenever you want, and you can access it from any computer in school. You can go into any computer room or a computer that's in a room, and you can get it from anybody's desktop.
We had our first year group go through with the additional science investigation, and we were really pleased with a 94.5% A to C for those students. Even more pleasing was the levels of their coursework, which for many students exceeded what their potential attainment would have been for their examinations. So we did hopefully find that by providing high quality digital images, digital software, that we're able to help students really improve their overall GCSEs.
I think it's like better because you can like watch it and understand like the science behind the experiment that you don't get to see occur when you do the experiment, and it just kind of explains it a bit more.
All the information's there really for you, and sometimes it's easier if the teacher's behind you to explain what's going on, but if we've done it like we have done today, where you see the reaction and then you see the actual reaction occurring on the computer, it's a lot easier than just seeing what actually happens.
And what were we measuring?
Pete Hoskins at Westborough High School in West Yorkshire is working with his Year 7s to create visual comic strip presentations that describe the experiments they've done.
It's part of a series of lessons that they've done on particles, and within that we've been looking particularly at modelling and trying to get across the idea that particles behave differently in solids, liquids and gases.
Can you make sure, please, that you've got
got goggles on.
Their practical investigation into the particle model involves looking at the viscosity of oil.
So the pupils simply had 2 temperatures of oil and then had to pour that through a funnel and then time how quickly each oil came through the funnel to actually see if the temperature affected the time.
So was it 4.90?
Yeah, Miss 4.90.
So you need to write that one.
We can talk about a whole range of things such as which variables we're changing, what are we measuring, what do we need to actually keep the same in terms of control variables. We can start to look at the quality of the data they collect and how they might interpret it.
So we've took one, so shall we not take another one?
How many did I say you need?
5.
Okay, including one of that. So if you've got one, how many more have you got to do? At least another
3.
3. Which of the 2 oils comes through the fastest? Hot or cold?
Hot.
Hot. So if that's the case, if you were to describe the oil as runny or less runny, which one would be the runniest?
Hot one.
The hot.
What does that tell
The class itself is our lower set class, and you've got pupils in there who would be level 2, level 3 in terms of national curriculum, and reading ages, which might be anything from 7 years old.
Remember, you've got to take your photographs.
And then, of course, we asked them to take a number of pictures. The focus of that, what we wanted was for them to familiarise themselves with the apparatus first and foremost, to then start thinking about what it was they were changing and what they were measuring, to start thinking about the actual procedure itself.
The laptops are then set up so the class can start using the comic strip software.
Now that should recognise it now, that's fine. The comic strip programme, it's really just a tool to produce comic strips, and as such, it's just a series of templates that you can actually use. As long as you've got some digital photographs there, you can drag them into the template and then add a whole range of speech bubbles and various effects as well. So, which of your pictures comes first?
This one.
Can you click and drag? Okay. And can you explain what you were doing there?
The cold oil.
You do the cold oil first. So get a speech bubble, put it in, drag it up. Okay. If you want to make the bubble bigger, then you can double click on the bubble and then just make it bigger. But try and just explain now what you were doing. So what did you say you were doing?
We were putting the cold oil into the filter.
So you would put the cold oil in. What were you measuring?
How fast
Okay, so write that in, okay?
we wrote our seconds, how much second did it, like the hot or cold, how long did it take to go down, and I'm writing it, this is the hot and that's the cold water, and which one went faster and stuff.
I need to do another picture of me, because that's a picture of me, but it's upside down.
Right, you can put it in here and you can spin it round. Put it in that one. We sat down and we thought about how we can actually go about trying to produce, in particular, assessments which would allow the pupils to put forward their understanding and to express their understanding other than something that was obviously just going to be paper-based because of the literacy levels. And they really enjoyed actually putting those strips together and actually looking at their own photographs. But it was the discussions, I think, that took place around that production of the comic strip which was particularly strong.
We're changing the...
You had 2 different types of oil, didn't you? What was the difference?
Hot and cold.
Right, hot and cold.
Hot.
And what were you then measuring?
The jug? No.
What
the
piece
oil?
of equipment were you measuring? What piece of equipment were you using to measure? As you poured the oil through, what do you start and stop?
Stopwatch.
Okay, so you're measuring what?
The stopwatch.
Oh, a stopwatch helps us to measure what?
The time that the oil dripped down.
Great, the time. So, what do you find out from your experiment? Which of the 2, the hot or the cold, seem to go through the quickest?
The hot.
The hot.
By 3 point something seconds.
I think that the majority of them did get it. I mean, they still need a little bit of coaxing. There are 1 or 2 pupils who I can see their understanding is still, not assured. There's still doubt in their mind, and so as a classroom teacher now, I can see who in the class actually has got a strong knowledge of particles and who is still unsure about it. So obviously that can now be addressed in future lessons.
The pupils go on to use some simple animation software that the teacher had set up to model the movement of particles in solids, liquids and gases.
The scratch animations were just an extension of some work that they've done on modelling already. And again, it was really done as an opportunity to assess their understanding of their previous lessons. And the visual nature of it, and also in terms of the audio and putting in the sound files, it really does show whether those pupils themselves really understand whether or not a particle in a solid might be vibrating or what it would actually look like.
What did you say to me before, though? You said it was what?
Like a smoke, but it's kind of like steam, a cloud.
Was it a gas? Is it going really, really fast?
No, so it's going slow. It's liquid.
So it's a liquid, so we need to change what to it?
The cloud bit.
And change it to what? A picture of?
A picture of what? That water.
Of water, good.
We made a conscious decision not to have a process where they would have to write a lot, because we just understood from the start that that wouldn't allow them to express their understanding. I think that the strength of it is not so much in the comic life strips and the experiment at the start, or indeed the scratch animations at the end. It's the two things together. And I think at the end of the process, when you sit down and they can actually see those animations on the Scratch program, and they can actually make those choices and decisions that they've actually got to make. That's when you really see if they understand how these particles are actually behaving.
So in the hot, the particles spread out, and in the cold, the particles be together.
Okay, so they're closer together, yeah? So in the hot, are they moving slowly or quickly or what?
They're moving quickly.
Okay, excellent. So we started to look at their ability to explain models of particles. They were coming out at level 4, whereas on a written test, the same pupils were level 3. So it was very powerful to us, and a great indicator of where we want to go for the future.